All right, kids. So we got shapes today. Let's talk about some shapes. All of this is based on the fact that there are lone pair and there are bonding pair. Lone pair are the electrons that are sort of already figured out. They don't need to be matched up when we're doing these Lewis structures. And then the bonding pair are the ones that are being shared between two atoms. And regardless of if they're bonding or lone pair, electrons still don't like each other. They repel each other, and because of that, they all need their own space. So valence shell electron pair repulsion, VESPR, is a way to understand these shapes and how they're influenced by the fact that all of these electrons are looking for their own space. And what we see is if you have only two areas of electrons around a central atom, those two areas are going to get as far away from each other as possible. And what we did in class is you saw that balloons act a lot like these electrons. If you only have two balloons and you try to put them next to each other, they'll make a line to be 180 degrees away from each other. So that's called linear when something like that happens. If you have three balloons or three areas of electrons around a central atom, they will go 120 degrees away from each other and do what's called trigonal planar. So let's take a look real quick at this in this situation. So here's linear, okay, and you can play with this. Everything's in a line. Your angle's 180 degrees. If you try to get them closer, they don't want to. They resist and go back to 180 degrees. Okay. If you add a third thing, now everything's 120 degrees, and you can see that everything's on the same plane. So you can get it so that basically everything looks like you could put a tray on top of it and it would be fine, right? There's no bump in the road there. So trigonal planar is when you have three things around a central atom, three areas of electrons. Now, if we add a fourth thing, because this is three-dimensional space, it doesn't go to a square. It actually goes to what's called a tetrahedral. And if you look at this from sort of like this angle, this one here is coming out toward you. And if you were going to put this into a cubicle box, this would be in the front part, the front corner of the box closest to you. Um, this would be in the front quarter of the box at the bottom and to the left. So this would be sort of in the right corner. This would be in the left front space. This one here would be in the back right corner. And this here would be in the back left corner in the upper part. So that's as far as these things can get away from each other in a three-dimensional space. And again, if you use balloons, you would see that that would happen with balloons. So if you put four balloons together, that's basically the same situation you would have. They would get as far away from each other as possible in three-dimensional space. So that's called a tetrahedral when you have four things like that around a central atom. If we introduce a lone pair, so take away one of these H's and put a lone pair in there, that lone pair still needs space from these electrons. And so because of that, it's called trigonal pyramid. And to take a look at that, that is, so if we take away one of these and replace it with a lone pair, so there's your trigonal planar, right? If we throw in a lone pair, it's going to push all that stuff down. So trigonal planar is like that, and trigonal pyramid happens when you put a lone pair in there and it pushes the three bonded atoms down so that they form more of a pyramid shape. So they're not on the same plane anymore. There's a little bit of a rise in that middle one, see? So these are on the same plane. If these are all on the table, this would be up off the table. If we get rid of that, then they all could hit the table at the same time. But with this on there, it pushes these down into what we call a trigonal pyramid. And then if we put two of these in and take one of these off, so this is what bent is. This is what water is. So oxygen's here and the hydrogens are here, and these lone pair are pushing those together. If those lone pair weren't there, we could be 180 degrees like we were before. But with the lone pair there, because the lone pair needs space, they're going to push those down into what we call a bent shape so that they're closer together, so that there's room for these electrons. Now, these angles aren't quite right. Based on what we've measured in labs, we know that the lone pair, because they're closer to the atom than a bonding pair. Think about it. These electrons are sort of between this atom and that atom, so they're kind of halfway between. Whereas this lone pair is legit on this atom. That's where they belong. So because lone pair are closer to the atom, they actually push these a little closer together. Um, so for bent, I think it's like 104. So these would be pushed about, I can't even do it, but like 104. And with trigonal pyramid, they'd be a little less, like 107, I think is what it is. So because these are closer to the atom, they actually push these down a little bit more than what's being seen here. So that would push these down. So this would be down a little bit toward the 107 with each other, if that makes sense. All right. So what you need to know is these shapes and their angles. So bent, like I said, it's a little less than trigonal pyramid, which only has one lone pair, and that's a little less than tetrahedral, which has no lone pair, only bonding electrons. But they all basically have the same amount of electrons trying to find space. So the way to remember this is if there are three atoms involved, it can be either linear or bent. If the central atom has no lone pair that needs space, then it's going to be linear. So this is your carbon dioxide or anything with beryllium, Be, which is the only reason we're teaching you Be is so that we can give you a linear situation. So beryllium only has two valence electrons, so it's going to be linear. Things would be bent if there's lone pair on that central atom. So your oxygens, your sulfurs, that kind of thing. Uh, those would be bent because those lone pair need space. And as we just saw, if your lone pair needs space, then it's going to bend those things closer together, right? So your lone pair are going to bend these closer together. Without them, it's 180 degrees. Okay, so same thing is true with trigonal planar. So if there are four atoms, it's either going to be trigonal planar or trigonal pyramid. Again, the only difference is there a lone pair or is there no lone pair on the central atom? If there's no lone pair on that central atom, then these will get as far away as possible in sort of the same plane. So that's why it's 120 degrees. And if you put that lone pair in there, it'll need space. So that's what I was just playing with here. Okay, so here's your no lone pair, trigonal planar, and then you put a lone pair in. It needs space. It makes more of a pyramid. Take it out, goes back to a plane, put it in, goes back to a pyramid. So the lone pair will push things into a pyramid shape. No lone pair, it'll stay planar. Then tetrahedral, that's just when you have five atoms. That's pretty easy. So five atoms tetrahedral, four atoms either trigonal planar or trigonal pyramid, depending on the lone pair. Three atoms either linear or bent. Again, lone pair will make it bent, linear will make it straight. So there are a couple that have more than four electron domains. So that's beyond what a noble gas would be. And these are kind of nutty. But we expect honors to know these. So 120 degree. So actually, let's just show you what that is. So there's trigonal bipyramid and octahedral. And it's basically trigonal bipyramid has five things going on and octahedral has six. So if you go back to this and you take this off and we just put two more on there, okay, so you can see how there's these three things that are sort of doing their trigonal planar situation, right? So these three are doing trigonal planar, which are about 120 each. And then the other two are doing, so I guess like this one and that one. I don't know why that moved, but these two are doing more of a like a 90 and a 90, right? So they're all in a straight line, and then you have three here, and that's what would happen. And it doesn't have to always be, I guess we do just do it bonding in this case. So you can do other stuff with lone pair, but basically that's the shape of five things connected. We can discuss that, why that happens if you want, but basically it has to do with having that D subshell available to put some electrons in. So that's five, and if you put six, you get what's called an octahedral. So an octahedral will have all of these 90 degrees, and then everything here as well. 90 degrees there, 90 degrees there. So it's 90 degrees all around. And you can play with this and convince yourself that's the case. So honors needs to know the more than four. Academic, you just need to know these. But basically, if there's a total of 6 atoms, it's trigonal bipyramid. And if there's a total of 7 atoms, it's going to be octahedral. All right, then. There you have it.